Lesson 8.4, Independent and Dependent Events. All right, independent and dependent events are two events with two outcomes. So we've been talking about single event and single outcomes. So now we have two events with two outcomes. Independent events is where one event does not affect the other event. Like rolling a dice and flipping a coin. They have nothing to do with each other. The probability of A and B both occurring is just the probability of A occurring times the probability of B occurring. Or the probability of A, given that B occurred, would be the probability of A and the probability of B, given that A occurred, to be just the probability of B. Which means if they are completely independent, this conditional probability is the same as its individual probability. So the fact that it's given B happened doesn't affect the probability, or given that A happened doesn't affect the probability. Whereas dependent events, one event does affect the other, and our probability of both of them happening is the probability of A times the probability of B, given that A already happened. And we do that because for B to happen and to get our probability, A has to already have happened. Otherwise, it doesn't much matter and we failed. For example, let's say a bag contains 6 pieces of paper numbered 1 through 6. You randomly select a piece of paper, replace it, and then randomly select another piece of paper. Use a sample space to determine whether the randomly selected a 5 first and randomly selecting an odd number second are independent events. Well, we can shortcut this. We replace it. That's going to indicate that it's independent events because the second draw has the same probabilities as the first draw. It's independent because you have 6 choices both times. So the first time you draw, you could get a 1 through 6. The second time you draw, you could get a 1 through 6. Sample spaces are the same. It's independent. All right, let's change the problem slightly. This time, we randomly select a piece of paper and set it aside. We don't put it back and then randomly select another piece of paper. Drawing 2 times is it independent or dependent? Well, this time it is dependent. The first draw has 6 choices. The second draw only has 5 choices because you set the first paper back and it did not get put back in the bag. So when some of the choices are removed, it's definitely a dependent event. Why don't you pause this and try numbers 1 and 5 on page 430. Number 1 is independent, and number 5 you should have gotten dependent. You can also use two-way tables to figure out independent and dependent events and make decisions. Let's say a store surveys customers with different ages, and the survey asks whether they want to see the store expand its toy department. The results, given as joint relative frequencies, are shown in the two-way table. Determine whether wanting to see the store expand and being less than 10 years old are independent events. Well, we are going to find the probability that were less than 10, given we have a yes. All right, why would we do that? Being less than 10 and wanting to see it expand, so that's the yes, they're independent. If this equals the probability of less than 10, then we have they're independent. Just thinking kids probably want the toy department expanded, so it's likely not. All right, so how do we do this? This would be the same as the probability we're less than 10 and a yes divided by the probability of yes. Remember, it's the conditional probability. It's the and on both of them on top and just the second one on the bottom. All right, so less than 10 and yes is 0.27. Just the yeses in total are 0.27, 0.06, and 0.23. It's 0.27 over 0.56. So when I divide those, we get 0.482. All right, so now let's compare that to the probability that the kid is less than 10, or the person is less than 10. All right, to be less than 10, that's those right there. That'd be the 0.27 plus the 0.09. Remember that those are already probabilities. And you get 0.036. So are those the same? No. So they are not independent. They are, in fact, dependent, as we expected, because, you know, the little kids are going to want to see more toys. The older ones are not. So it's definitely dependent. If it was independent, the conditional probability and the non-conditional probability would be equal. Why don't you pause this and try number 11? The answer should be, for number 11, is independent. All right, so here's a spinner numbered 1 through 8. We're going to find the probability that we get an even number on our first spin and a number less than 3 on our second spin. So first of all, we have to decide whether this is independent or dependent. So does spinning it once change what's going to happen when you spin it again? Nope. So that makes it independent because the spinning doesn't affect what happens next. So we want the probability that we get an even number and then a number less than 3. All right, since this is independent, we can just multiply the two things separately. So we can multiply the probability of getting an even with the probability of getting less than 3. Even, well, half the numbers are even. There's 4 spaces, the 2, the 4, the 6, and the 8. So that's 4 out of 8. And the numbers less than 3. There's 1, 2, 3 of those. Well, actually, not 3. Sorry, it's just 2 of those. So less than 3, so we're not including the 3. That's 1/2 times 1/4 is 1/8, which is 0.125. So probably not likely to happen. Why don't you pause this and try number 13. The answer should be 0.028, which is really not likely to happen. All right, 9 women and 6 men are on a committee. One person was randomly selected to be a chairperson and a different person was randomly selected to be the treasurer. Find the probability that both events A and B will occur. All right. So we want the probability that the chairperson is a man and the treasurer is a woman. So is this going to be independent or dependent? Well, after you choose the first person, there are less people to choose from for the second thing. So that does make it dependent. So this would be the same as the probability of getting a man for the first thing times the probability of getting a woman, given that we already chose a man. All right, so man, there are 6 men out of the 15 people. And now, after we have chosen this first man, who happened to be the chairperson, we want to pick a woman. Well, there are 9 women left, but only 14 people left, not 15, because we already chose one of them. So there's only 14 people left. And that gives us 0.257 when we multiply it together. Why don't you pause this and try number 15. The answer should be 0.147.